Hi, this is Database Management class, Chapter 2, Modeling Data in the Organization. So in this chapter, we're going to study several definitions of terminology, and also we will study importance of data modeling. And also, we will study how to make good name and definition for entity relationships and attribute. Also, we will study unary, binary, ternary relationships difference, and also we're going to study model different type of attribute, entity relationship, and cardinalities. And then we will study the many-to-many relationship converted to associative entity, and we're going to study time-dependent data modeling using timestamp. Entity relationship model construct. The important thing is the terminology, entities, relationships, and attribute. Actually, the entities, there are entity instance and entity type. Person, place, object, event, concept. Usually these all correspond to a row in a table. This is entity instance. And then the bigger concept, the collection of entity, often correspond to a table. We call this entity type. And then relationships, relationship instance, link between entity, correspond to primary key, foreign key, equivalencies in related tables. And relationship type, category of relationship, link between entity types. And then attribute, usually properties or characteristic of an entity or relationship type, often correspond to a field in a table. The figure 2-1 sample entity relationship diagram. You can see, there are supplier, and then customer, and then product and order. So actually in this figure, we have to study in this class about entity, and then entity type, and then the cardinality, the mandatory many, and then optional many, mandatory one, and optional many. So you can see mandatory one, optional one, and mandatory many, optional many. So the kinds of thing, we're gonna study. So actually in this picture, the entity relationship diagram include rectangle representing entities, and lines between the entity represent relationships. So relationships have cardinalities, which can be one-to-one, one-to-many, many-to-many. In addition, on each side of relationship, you can specify that it is mandatory or optional. A good business rule is actually business rule appears possibly implicitly in description of business function, event, policy, unit, stakeholders, and other objects. This description can be found in interview note from individual and group information system requirement collection session, organizational document, personnel manual, policies, contract, marketing brochures, and technical instructions, and other sources. Rules are identified by asking questions about the who, what, when, where, why, and how of the organization. Gathering business rules require good interviewing and listening skill. As a database analyst, you will ask questions about the who, what, when, where, why, and how of the organization. You will need to be persistent in clarifying initial statement of rules because initial statement may be vague or imprecise, so this is an iterative inquiry process. So a good business rule is declarative, what, and precise, clear, agreed upon meaning, atomic, one statement, consistent, internally and externally, expressible, structured natural language, distinct, non-redundant, business-oriented, understood by business people. A good data name is the data object must be named and defined before they can be used unambiguously in a model of organizational data. Data name refer to the names of entity, their attribute, and their relationship, which are the data object. These names should be meaningful to the business interest and operation. In a sense, data names should be self-documenting, which means they should obviously capture the essence of the data object. So a good data name is related to business, not technical characteristics. And also, a good data name is meaningful and self-documenting. And then a good data name is unique. And a good data name is readable. And then a good data name is composed of words from an approved list. A good data name is repeatable. A good data name is written in standard syntax. Data definition. It is difficult to obtain a universally agreed upon the data definition. So you may want to use multiple definitions to cover the various situations, or alternatively use a very general definition that will cover most situations. With data definition, as with most organizational knowledge, the person who controls the meaning of data controls the data. Thus, the definition of data is a source of organizational power. The explanation of a terminology or fact. So terminology, word or phrase with specific meaning. Fact, association between two or more terminologies. Guidelines for good data definition. A concise description of essential data meaning gathered in conjunction with system requirement, accompanied by diagram, achieved by consensus, and iteratively refined. Entities. It is important to distinguish an entity instance from an entity type. For example, an entity may be John Doe, a particular person, but the entity type is person as a concept. When you develop entity relationship diagram, the boxes represent entity types, not entity instances. Although we use the word entity when describing entity relationship diagram, what we are really talking about is entity types. Entity is a person, a place, an object, an event, or a concept in the user environment about which the organization wishes to maintain data. Entity type, a collection of entities that share common properties or characteristics. Entity instance, a single occurrence of an entity type. Entity type and entity instance. Figure 2-3. Entity type employee with two instance. Entity type employee. Here we see the distinction between an entity type and an entity instance. The entity type is represented in the first two columns of this figure. It concludes the name of the various attributes. Remember what it talked about regarding data name as well as the types of data. By contrast, the third and fourth column represent two entity instances. These would be actual record or row in the final database table that implement this entity type. An entity should be an object what will have many instances in the database. An entity should be an object that will be composed of multiple attributes. An entity should be an object that we are trying to model. An entity should not be a user of the database system. An entity should not be an output of the database system. A common mistake people make when they are learning to draw entity relationship diagram, especially if they are already familiar with data process modeling, such as data flow diagramming, is to confuse data entity with other element of an overall information system model. A simple rule to avoid such confusion is that a true data entity will have many possible instances, each with a distinguished characteristic, as well as one or more other descriptive pieces of data. Figure 2-4. example of inappropriate entity. You can see a system user, treasurer, and the output expense report shown as an entity. So this is inappropriate entity. So entity relationship diagram with only the necessary entity, just account and expense. Yeah, actually the system user or output, the treasurer or expense report, it should not be entity. Yeah, this figure illustrates a mistake, many novices will make. The treasurer is a user of the system, and the expense report is an output of the system. Neither of these are entities that should be represented in the database or the entity relationship model. The entity relationship model should represent the objects that are of interest to the user and that will be displayed in the system output. Strong versus weak entity and identifying relationship. Most of basic entity type to identify in an organization are classified as strong entity types. A strong entity type is one that exists independently of other entity types. So sometimes these are called independent entity type. In contrast, a weak entity type is an entity type whose existence depends on some other entity type. So these are sometimes called dependent entity type. Strong entity exists independently of other types of entity, has its own unique identifier, so identifier underlined with a single line. Weak entity, dependent on a strong entity, identifying owner, cannot exist on its own. Weak entity does not have a unique identifier, only a partial identifier. Weak entity, entity box, and partial identifier have double line. Identifying relationship links strong entity to weak entity. Figure 2-5 example of a weak identity and its identifying relationship. Weak entity with identifying relationship. This figure shows an entity relationship diagram depicting an identifying relationship between an identifying owner, the employee, and the weak entity, the employee's dependent. Note that the dependence identifier is only a partial identifier. The full identification requires the identifying owner's identifier as well. Also note the double lines that distinguish the weak entity and the identifying relationship. So you can see employee, yes, single line underline, employee ID is identifier, yeah. But double line rectangle and double underline, these are partial identifier. And also double line, yeah, shows the weak entities relationship. So strong entity, weak entity, identifier, partial identifier. Yeah. Guidelines for naming entity. In addition to general guidelines about naming and defining data object, there are some specific guidelines for naming entity type. These are listed here. Singular noun, specific to organization, concise or abbreviation for even entity, the result, not the process, name consistent for all diagram. Guidelines for defining entity. In addition to general guidelines about naming and defining data object, there are some specific guidelines for naming entity type. So these are listed here on X is and also describe unique characteristic of each instance and explicit about what is and is not the entity. And when an instance is created or destroyed and changes to other entity type, and then history that should be kept. Attribute. In naming attribute, we use an initial capital letter followed by lower letter. If an attribute name consists of more than one word, we use a space between the words and we start each word with a capital letter. For example, employee name or student home address. In entity relationship diagram, we represent an attribute by placing its name in the entity it describes. Attribute property or characteristic of an entity or relationship type. Classification of attribute, required versus optional, simple versus composite, single value versus multi-value, stored versus derived, identifier. Figure 2-6 required versus optional attribute. The figure illustrates the various properties of an entity attribute. Required attribute must have a value, whereas optional attribute could be null. Note that the identifier is always required. In this case, the student major is optional because a student may not yet have declared a major. All the other attributes, however, are required. So you can see, the student ID, name, home address, home city, home state, home zip code are required attribute, but major is optional. So require must have a value for every entity or relationship instance with which it is associated. Optional may not have a value for every entity or relationship instance with which it is associated. Figure 2-7, a composite attribute. Composite attribute, an attribute that has meaningful component part, sub-attribute. Component attribute, composite attribute. Sometimes many attributes are related to each other, such as the element of an address. In this case, they can be grouped into composite attribute. For simplicity, we can refer to the employee address, but if we want more detail, we can break it into street, city, state, and postal code. So this way, we have the option to describe the attribute at a macro or at a micro level. Note the use of parentheses for encompassing the component or a composite attribute. So you can see these are composite attribute, and then this is the component attribute. Figure 2-8, multi-valued and derived attribute. A multi-value attribute is not the same as composite attribute, although novices may confuse these terminology. A composite attribute is one that has many parts, such as an address composed of street, city, state, and zip code. By contrast, a multi-value attribute is one that can have many different values, such as an employee being able to do many things. Note that a derived attribute is not one that is physically stored in the database, but rather one that is calculated based on the value of another. The length of time employed or a person's age are classic examples, as they are calculated based on a fixed starting point, date hired, or birthday. Attribute can be both composite and multi-valued, and even also derived. So these are distinct concepts. So multi-valued may take on more than one value for a given entity or relationship instance. An employee can have more than one skill. Derived values can be calculated from related attribute value, not physically stored in the database. Years employed calculated from date employed and current date. So multi-value attribute and derived attribute. Identifier keys. Every entity type should have an identifier attribute. No two instances of the entity types may have the same value for the identifier attribute. For example, a person, employee, student, etc. cannot rely on the first and last name to be an identifier, because many people could have the same name. Later, the identifier should be something like an employee ID, a social security number, or some other absolutely unique type. So identifier, an attribute or combination of attribute that uniquely identify individual instances of an entity type. Simple versus composite identifier, candidate identifier, or attribute that could be an identifier. It satisfies the requirement for being an identifier. Criteria for identifier. An identifier in the entity relationship model will eventually become a primary key in the resulting database table. We'll see this later chapter. Identifiers are required, so cannot be devoid of value. This value should also be constant and unique. Consider an employee ID or social security number. These do not change. However, a person's name or home address could change. Similarly, several people could have the same name or address. Choose identifier that will not change in value, will not be known. Avoid intelligent identifier. Example, containing location or people that might change. Substitute new simple keys for long composite key. Figure 2-9, simple and composite identifier attribute. Simple identifier attribute, student, student ID, identifier, and required. Composite identifier attribute, composite identifier, flight number, date, In the entity relationship diagram, an identifier will be underlined. Note also that required attributes are typically boldface. So all identifier will be boldface as well. If an identifier is composed, then all its component parts are required. Naming attribute. As with all other data objects, there are guidelines for naming and defining attributes. These are listed in this slide and the next. A common naming format is entity type, name, class, where is an optional clause and indicate that the clause may repeat. Entity type name is the name of the entity with which the attribute is associated. The entity type name may be used to make the attribute name explicit. It is almost always used for the identifier attribute. Example, custom ID of each entity type. Class is a phrase from a list of phrases defined by the organization that are the permissible characteristics or properties of entity, or abbreviation of these characteristics. For example, permissible value and associated approved abbreviations for class might be name, identifier, date, or amount. Class is required. Qualifier is an optional phrase from a list of phrases defined by the organization that are used to place constraint on classes. Name should be a singular name or noun phrase. Name should be unique. Name follow a standard format. Similar attribute of different entity types should use the same qualifiers and classes. Defining attribute. State what the attribute is and possibly why it is important. Make it clear what is and is not included in the attribute value. Include aliases in document. State so values. State whether attribute value can change one set. Specify whether required or optional. State minimum and maximum number of occurrence allowed. Indicate relationships with other attributes. Modeling relationship. Relationship type versus relationship instances. The relationship type is model as rank between entity type. The relationship instance is between specific entity instances. Relationships can have attributes. These describe features pertaining to the association between the entity in the relationship. Two entities can have more than one type of relationship between them. Multiple relationship, associative entity, combination of relationship and entity. Figure 2-10, relationship type and instances. This figure illustrates the difference between relationship types and relationship instances. The entity relationship diagram depicts types. It depicts both entity types and relationship types. The metadata of the database is model based on the entity types. The actual data that goes into the database are instances, both relationships and entity instances. So you can see there are employee and course. These are entity type. And then employee Chan, Melton, through Gosling, course C++ Java through SQL. And then between entity type, there are relationship type, and between entity instance type, there are relationship instance. Degree of relationship. Most relationships are of binary degree, but it is possible to have any number of entities involved in a relationship. Ternary refers to three. If you have more than that, it is sometimes referred to generically as an n- ary relationship. Degree of relationship is the number of entity types that participate in it. Unary relationship, binary relationship, ternary relationship. So from figure 2-2, degree of relationship. One example of a unary relationship would be supervised subordinate relationship, which exists between employees. An example of binary relationship may be an employee working in a department. to entity. And ternary relationship or ternary relationship may involve a product being shipped by a particular supplier to a particular warehouse. So, entity of three different types involved in the same relationships. Cardinality of relationships. One to one, each entity in the relationship will have exactly one related entity. One to many, an entity on one side of the relationship can have many related entities, but an entity on the other side will have a maximum of one related entity. Many to many entities on both sides of the relationship can have many related entities on the other side. Figure 2-12, example of relationship of different degree. Yeah. Unary relationship. Yeah. A person is married to person one to one. An employee is manages employee one to many. And then team stand after team one to one. Although this figure of unary relationship show only one to one and one to many cardinalities, it is also possible to have many to many unary relationships. For example, consider a person entity with a friends relationship. A particular person can have many friends, and each friend could in turn have other friends. This is different from the one-to-many relationship of employees. Although a supervisor could manage many subordinates, typically a subordinate only reports to one supervisor. Figure 2-12, example of relationship of different degree binary relationship. Employee is assigned parking place one to one. Product contains product. Product line contains product one to many. Student register for course many to many. Here a binary degree relationship with all the different possible cardinality. Ternary relationship. The vendor ship some part from some warehouse. Yeah. For example, an instance is vendor X supplies part C to warehouse Y with a shipping mode of next day air and a unique cost of $5. The cardinality of this ternary relationship is many to many to many. In other words, each vendor could supply many parts to many warehouses. Each part could come from many vendors and be housed in many warehouses. Each warehouse could have many parts from many vendors. The dash sheet 9 is a way of representing the attribute of the relationship for a given vendor supplying a given part to a given warehouse. There is a shipping mode and a unique cost. Each of these ternary relationship instances could have its own shipping mode and unique cost. Figure 2-15, using relationship and entities to link related attribute. Multi-value attribute can be represented as relationships. Multi-value attribute versus relationship be a bill of material structure. In this figure, we see two examples of multi-value attribute. On the left, on the right, we see separate entity with relationship. The top figure shows a simple multi-value attribute, whereas the bottom figure shows a composite multi-value attribute. Note that on the right, it is explicit that there are many-to-many relationships. For example, although the left side shows that a course can have many prerequisites, there is nothing explicit showing that a course could itself be a prerequisite for multiple other courses. Similarly, on the left, it is explicitly shown that an employee can have many skills, but it is not explicitly shown that many employees can share the same skill. The figures on the right, however, do make this fact explicit. The right side of its figure is in Microsoft Visual Notation. So you can see the course. Yeah, there are multi-value prerequisite, and then employee, and employee name, and skill. There are skill code and skill title, skill type. These are, yeah, composite attribute, also multi-value attribute. Yeah. Cardinality constraint. Sometimes it is required for an entity to have each related entity and sometimes not. Also, it is possible for there to be a limit to how many related entities a given entity could be related to. Cardinality constraint, the number of instances of one entity that can or must be associated with each instance of another entity. Minimum cardinality, if 0, then optional. If 1 or more, then mandatory. Maximum cardinality, the maximum number. Figure 2-17, example of cardinality constraint, mandatory cardinality. Yeah, patient has recorded patient history. Yeah, these are mandatory. So Mark visit first, and Sarah visit first and visit second, and then else, yeah, visit first time. Yeah. Note that hatch mark versus the circle. The hatch mark illustrates mandatory cardinality, whereas the circle represents optional. This figure indicates that each patient must have had at least one patient history, mandatory, and could have many many. By contrast, each patient history visit record must be associated with exactly one patient. Note that in all these entity relationship diagram, cardinality is represented using something called cross-put notation. The three prongs on the many side of the relationship is called the cross-put. There are other possible notation for entity relationship diagram. For example, Microsoft Visor by default shows an arrow from the many side to the one side, although you can change it to cross put notation. Figure 2-17 example of cardinality constraint. One mandatory, one optional. So H means mandatory, circle means optional. So employee is assigned to project. Yeah. Some person is assigned to many projects, but somebody is not assigned to any of the project, like Pete or Heidi. Yeah. So this figure shows a binary many-to-many relationship. In this case, one side is mandatory and the other is optional. Here, every project must have at least one employee assigned to it, but it is possible for an employee not to be assigned to any project. Optional cardinality. Person is married to person. Circle means optional. So maybe Charlie is married to Alice. Meg is married to Kathy. But Dawn is not married to anybody. Also, Pratt is not married to anybody. This is a unary one-to-one relationship. According to this, a person could be married to one-to-one or no other person. This figure rules out polygamy. Can you see why? How would we be able to allow polygamy in this entity relationship diagram? We should use many-to-many. And Don and Fred are single. Charlie is married to Alice, and Meg is married to Kathy. Figure 2-12.1, example of multiple relationship. Employee and department. Yeah. Employee, yeah, supervised by, also supervise employee, and employee manages department, and employee works in department, and department has worker, and department is managed by employee. Here we see one-to-many unary relationship between employee. It shows that a given employee may have exactly 0 or 1 supervisor and could supervise any number of other employees or none at all. We also see two binary relationships between employees and department. First, each department must have at least one and possibly many employees. Each employee must work in exactly one department. Also, each department has exactly one employee as a manager, and each employee can manage at most one department, or possibly none at all. The figure illustrates that there could be multiple types of relationship between the same two types of entity. Professor and courses fixed lower limit constraint. Again, we see multiple relationship between two entities. This time between professor and courses. The is qualified relationship is of binary degree and mandatory many-to-many cardinality. A professor must be qualified to teach at least one courses, and their course must have at least two qualified professor. This is a fixed lower limit constraint. The other relationship is actually implemented via what is called an associative entity called schedule, which has an identifier attribute called semester. We will shortly talk about associative entities in more detail. This associative entity is implementing a many-to-many relationship between professor and courses, indicating that a particular professor may be scheduled during a particular semester to many courses and vice versa. Associative entity. When should a relationship with attribute instead be an associative entity? All relationship for the associative entity should be many. The associative entity could have a meaning independent of the other entity. The associative entity preferably has a unique identifier and should also have other attributes. The associative entity may participate in other relationships other than the entities of the associative relationship. Convert ternary relationships to associative entity. Figure 2-11 Associative entity. An associative entity is an entity. It has attribute. It is also a relationship. It serves to link other entities together in a many-to-many relationship. Attribute on a relationship, an associative entity. You can see there are employee, complete, course, and we need the attribute date complete, and then we can change associative entity. Employee has certificate, the certificate number, and then date complete. So the certificate number is identifier. In figure A, the date complete attribute pertains specifically to the employee completion of a course. It is an attribute of the relationship. The relationship simply states that an employee complete a course on a particular date. The completion is represented as a relationship and is not an entity unto itself. In figure B, the simple relationship has been replaced with an associative entity. A certificate is considered to be an entity unto itself, and in fact, even has a unique identifier attribute. An associative entity is like a relationship with an attribute, but it is also considered to be an entity in its own right. Note that the many-to-many cardinality between entity in figure 2-11a has been replaced by two one-to-many relationships with the associative entity. The associative entity is always on the many side of the relationship. It links one-to many relations has been replaced by two one-to-many relationship. Figure 2-13 representing a bill of material structure. Two ways to represent a bill of material structure. Many-to-many relationship. Item has component associative entity, used in assembly, has component in A and C. We see another contrast of using a relationship with attribute versus an associative entity. Here, a unary many-to-many relationship is converted into two one-to-many relationship between the item entity and the bill of material structure associative entity. Note that effective date is a partial identifier, which implies that bill of material structure is a weak entity with respect to item. A bill of material is a hierarchy of items. Here, bikes are composed of handlebars, transmission wheels, etc. Transmission include their own support, brakes, and derailleur. Two item bill of material structure instances. Unary relationship, especially one-to-many or many-to-many, often depict hierarchies. Bill of material is one simple. Another example is a supervisor relationship between employee entity in figure 2-12.1. That relationship also depicts a hierarchy, this time of employee. Figure 2-18, cardinality constraint in a ternary relationship. The three relationships are marked by their mandatory or optional constraint. Number one states that a vendor may or may not supply part to warehouse. Number two states that each part must come from a vendor and go to a warehouse. Number three says a warehouse must have at least one part from a vendor. It is recommended that ternary relationship with attribute be converted into associative entity. Although figure 2-12c works to depict the general ternary relationship, it is insufficient for depicting the mandatory or optional cardinality as we see here. So there are vendor, part, and warehouse, supply schedule, shipping mode, and unique cost. Figure 2-19, simple example of time stamping. Timestamp, a time value that is associated with a data value, often indicating when some event occurred that affected the data value. The price history attribute is both multi-value and composite. Product, product ID, price history, effective date, price. So you can see timestamp. Timestamps are useful for keeping historical data. In this case, we see a way of keeping track of price change over time for product. Can you think of how the price history could be represented as a separate entity instead of a multi-value attribute? What would be the cardinality of the relationship between product and price history? 1-2, it should be 1-to-many. Figure 2-22 data model for Fine Valley Furniture Company in Microsoft Visual Notation. Actually, Yeah, we will study in this class, yeah, during our semester. So as you can see, data model can be quite comprehensive, including many different entity and relationship. So different modeling software tool may have different notation for the same construct. So we will call it a day. Yeah, long class. Have a great day. Yeah. Good job.